We have trained ourselves to believe that for machines to think, we have to set the physical world on fire. Modern computing operates as a brute force industrial process, ripping through gigawatts of electricity to power every prompt, every inference, and every digital decision. To sustain this hunger, sprawling concrete footprints are rapidly consuming rural landscapes. We are building server farms so massive they require dedicated nuclear reactors, pushing regional power grids toward total collapse under their sheer thermal weight. The core problem lies in how these systems operate. Modern AI models work by probabilistic guessing. They approximate answers, which introduces tiny errors, or drift, at every single step. To keep that drift from devolving into a total hallucination, the system burns an immense amount of energy running constant mathematical corrections. When a major tech firm announces a new 100 megawatt data center, they often frame it as an engineering marvel. It is actually a symptom of failure. It is a monument to an architecture that can only scale by consuming exponentially more resources to fix its own internal chaos. We are trying to map an infinite digital future onto a finite physical reality. You can write as many lines of code as you want, but you cannot negotiate with thermodynamics, and you cannot cheat the global supply of electricity. The infrastructure of the next century, autonomous ocean cities, multi-agent drone grids, precision climate models, cannot function if the underlying computation drains its host grid to death. A research group called Oikonomia architecture has engineered a way out. Instead of scaling hardware to outrun the chaos, they change the underlying math, abandoning probabilistic guessing entirely for a deterministic geometric structure. They call this a reversible substrate. This means the system calculates by preserving its exact structural state, both forward and backward in time. On the left, you see the traditional probabilistic method, a messy cloud of data that requires constant energy to wrangle. On the right, the reversible substrate uses a multi-scale geometric grid. The information smoothly expands and contracts, never losing its shape. Because the math is naturally reversible, data is never lost. You can run tens of thousands of complex simulation steps, and the system retains perfect structural coherence. It doesn't require constant algorithmic intervention to keep the information intact over massive time horizons. Without the need to guess, correct, and rewrite its own errors, the energy requirement plummets. The hardware is no longer spending gigawatts trying to reach a consensus. The correct state is already built directly into the geometric law of the operator. Trust, auditability, and accuracy stop being things we have to buy with massive utility bills. When the math preserves its own structure natively, stability becomes a hard mathematical guarantee. This shift in physics ensures that as system capability grows, the hardware footprint remains linear. You've decoupled intelligence from physical mass. Traditional AI relies on transformers. As you feed them longer sequences of data, they quickly lose track of the plot, demanding massive memory overhead until they eventually collapse. Oikonomia's deterministic operator avoids this trap. Take a look at this chart tracking world state accuracy over 100 million tokens.
The red line is the standard transformer, which plunges to 48% accuracy as its memory window fills up. The flat line at the top is the fractal operator. It processes the exact same 100 million tokens with zero hallucinations, zero contradictions, and absolute semantic consistency. The reason that line stays flat is a property called constant memory transport. Instead of memorizing an ever-growing list of past events and ballooning its memory footprint, the substrate processes information as a continuous streaming flow, keeping the actual memory pressure near zero no matter how massive the task becomes. By holding that memory footprint constant, the traditional hardware constraints vanish. You can execute civilization-grade intelligence and trillion-token workloads efficiently on standard commodity GPUs. The system actually gets better as it grows. Thanks to a mathematical law called superlinear efficiency, the larger and more complex the computational grid becomes, the more efficiently the operator moves data through it. Once you break the exponential energy tax of probabilistic AI, the math dictates a very clear outcome. The massive 100 megawatt data center becomes completely obsolete for planetary scale operations. A computational layer this stable has implications far beyond processing text. It allows us to deploy digital intelligence directly into extreme, high-stakes physical environments. In aerospace, this exact primitive serves as a new control architecture. Because the math calculates states perfectly forward and backward, a drone swarm can execute instantaneous maneuvers, like snapping into a stable inverted hover with zero drift and zero oscillation. It doesn't rely on classical predictive control. It physically expresses the geometric law. Out on the open ocean, this intelligence becomes the load-bearing control system for floating infrastructure. In hardware-validated simulations of autonomous megacities, the substrate handles real-time wave field prediction and ballast adjustments, stabilizing massive physical structures through continuous ocean turbulence. By applying this fractal update law to physical materials, we can engineer a computational metasurface that manipulates light at the algorithmic level. It collapses photon escape pathways, forcing light particles to dwell inside the material longer before they can bounce away. This structural trap yields a 310% increase in solar absorption without requiring a single new chemical additive. Whether coordinating a high-altitude research platform, a floating deep-sea district, or a planetary energy grid, these are no longer silo technologies. They are diverse physical machines operating on the exact same drift-free computational language. The massive infrastructure projects of the next century cannot rust on algorithms that guess and hallucinate. They require an underlying intelligence that is as immutable, stable, and predictable as physical concrete. The era of brute force intelligence is drawing to a close. Computation is moving past its role as an unstable, energy-devouring parasite. It is becoming a quiet, widely distributed utility that sustains the physical world instead of consuming it. Engineered correctly, this computational law provides the immutable scaffolding required to rebuild the world.